Good afternoon and welcome to this Chemistry World webinar. Today we're looking at how you can start being predictable and improve your experimentation. This is a webinar delivered in partnership with JUMP, who we work with a great deal to try and find ways to make your science and your chemistry that bit better, that bit more efficient, to make your own experiments that bit better for you. So today we're going to see how modern experimentation methods can increase your process understanding, allowing you to develop new products and boost your research and development output. We're going to be looking at a software demo and in particular a case study which will show how chemical technology development startup Novomer transformed their experimentation strategy with state-of-the-art statistical methods in a way that not only streamlined their R&D processes, but ultimately led to its successful acquisition. So over the course of the next hour, we're going to see how easy it is to get started with methods that streamline your work and yield more reproducible results. We're going to see how to increase product or process understanding through modern experimentation and how to motivate your organization to give that modern experimentation a try. Now, before we move on to the content itself, let me just talk to you about GoToWebinar, which is the platform that we've chosen to use. So I can see plenty of you have already logged in. The most important thing you need to know about GoToWebinar is that you can use it to ask questions. So down at the bottom of the GoToWebinar column, there should be a questions box, and I can see already that we've had a few people who have asked questions. So any questions you have at any point throughout the webinar, just pop them in that questions box at the bottom and we will make sure that they get to our speaker. And we've got a few resources available that will help you really make the most of what you learn in this webinar. So let's get them up on screen now. A few things that you should find very helpful. The start being predictable, improve your experimentation experience can be improved by, for example, doing the statistical thinking for industrial problem solving course, which is available on JUMP's website. The URL is there, and we will also fire that out as a click through to all of you just now. So the statistical thinking for industrial problem solving, it includes a module on design of experiments, which is largely what we're talking about today. And there's online certifications upon completion. It's a really useful course to do to get you a full background understanding of how these stats work, why they work, how they can improve your processes. If you'd like to have a go at the things that you will see in today's demonstration, then JUMP has a 30-day free trial for anyone interested in trying it for themselves. Again, the URL is on screen now, but we're also sending it out in the chat box so you can copy and paste it or just click on it there and find that online. And finally, if maybe you're already using JUMP but you want to take the next steps and get a bit better at what you're doing, the JUMP online community, which is at community.jump.com, is a really good resource to get help and support in answering your questions from almost 20,000 members who use JUMP to make their own work that bit more efficient. So we will share those resources again at the end of today's webinar if you didn't catch them, but they should have appeared in the chat function for you there if you want to click through now and then have a look after today's webinar, and you can really help to capitalize on what we'll do over the course of the next hour. Now, our speaker today is Hadley Myers. He's a systems engineer for JUMP. He's got 10 years combined research and manufacturing experience in photovoltaics. He previously worked at Smith Thermal Solutions and Heliovolt, and he served on the technical advisory board for On-Peak Power. So he's got a broad range of experience. He knows how the modern experimentation processes we are looking at today can really make a difference to your organization. That's quite enough from me. Do keep those questions coming in. We'll have a couple of polls as well, so we get to learn a bit more about you as well as learning more about Hadley. So I will step back now, leave Hadley to it, and we'll speak to you again at the end of the webinar. Thank you very much.
All right, well, thank you very much, Ben, and hello to everyone joining us online, wherever you are, whatever time it is where you are. If you're using your lunch hour to watch this, we really appreciate it. So before I really jump into it, I'd just like to take a few seconds to talk about what the benefits of design of experiments are and why companies care about them and why you should listen to this presentation. So I've listed out some of the benefits here, but what this really boils down to is that companies use design of experiments to shorten development cycles so that they could speed products to market. At this point, I think I'd just like to mention something. So one of my neighbors is doing some work on their kitchen. I apologize for the noise. I think it'll be short. Hope it's not too distracting. So just to move on, as I say again, companies use design of experiments to shorten development times to speed products to market. They can do this at reduced costs and predictably. And so this is why we see people using design of experiments not only as a technical tool, but also as a project management tool, right? If you can predict how many experimental runs a development cycle will take at the start of the cycle, then you can budget for it and allocate resources effectively. So this is why companies care about it. This is why companies seek out employees that have these skills, why they invest in training to bring up the skills of their current employees, and why it's even required in some fields. For example, why regulatory agencies require it in drug development applications. So that's how companies benefit from design of experiments. At this point, I think I'd like to hear from you. I'd like to know, what is it that you hope you're going to gain from this and how your company will benefit? And so at this point, Ben, can we bring up the first poll question, please?
We can indeed. So this is the first interactive bit of today's webinar. We're asking you which benefit of design of experiments is most relevant to your organization, or what would you really like to see to get out of a design of experiments approach? So do please pick one of these answers. Is it a better understanding of your processes and products? Is it the ability to optimize and therefore perhaps save time or money or feedstock, for example? Do you want to get more reliable results so you know that you're reporting better? Do you want to get those results faster, or is it a little bit of everything? So what we need to do is just get some examples from you, or see what it is that you think. We're still collecting the responses at the moment. We're going to give it a few more seconds to let a few more of you vote. We have had a couple of questions, one of which I can answer straight away. Anybody who attends this webinar will be sent a certificate confirming that you attended. It might take us a couple of days to get that out to you, so don't worry if it doesn't arrive straight after the webinar, but you will get a certificate. That's our way of saying thank you for attending the webinar. I think that's probably just about enough time for people to vote, so let's close it down, share the results. Let's see what people thought. Well, most people say it's a little bit of everything. That's probably no big surprise, I'd say there, Hadley, that most people want to better understand their products. They want to optimize. They want the results to be more reliable. It seems people aren't in a rush at the moment, which is nice, but most people want a little bit of everything. Is that sort of what you expected to see?
Yes, it is. There's a wide range of reasons and benefits people gain from design of experiments. They're all equally valid. So it doesn't surprise me to see that people are interested in all of these. And it could be that you're interested in different benefits at different times. And so that's why it's important to understand these techniques and keep them in mind as you move forward.
Thank you very much to everybody for completing the poll there. We'll close those poll results down now. There is another poll coming up later, so we will still learn a little bit more about our audience as we go through the presentation.
Yeah, absolutely. So very briefly, what we're going to be looking at today is, in order to understand design of experiments, I think it's important to compare it to its alternative, which is the one factor at a time approach. So you'll see what the failings and insufficiencies of that approach are and why design of experiments is better. After that, we'll look at a case study that I actually was, that happened to me in my past. You'll see how knowledge of design of experiments not only benefited me, but benefited the company I was working for as well as our customer. And then we'll look at a company called Novomer and what they did to generate a 21-run design that ended up allowing them to optimize a process, which they then spun off for $100 million. One thing I'll mention now is, if I just bring this over here, so this story is detailed on our website. You can find it here. If you go to the website and then click Jump into Action and Customer Stories, from here you can find a bunch of different case studies of how other people have benefited by design of experiments, as well as a host of other applications. And so the Novomer case study can be found right there. Maybe it's relevant for you if you're joining us here. Maybe one of these others is relevant. So I encourage everyone to take a look at those. And then finally, we'll talk about what you can do once you've completed your designed experiment, once you've generated knowledge for an organization, what steps can be taken to ensure that that knowledge isn't lost? So we'll look at some solutions for that. And then at the end, we'll point you to some resources. So in order, just make this a little bit bigger. In order to understand design of experiments, I think it's important to take a look at the alternative. Now, one factor at a time approach was what I was taught in school, in high school. Probably a lot of you were as well. It makes sense. It's intuitive. It's easy to understand. If you want to know the effect of one factor of your process, you need to keep everything constant, only change one factor at a time. Otherwise, you won't know which one affected your process. It makes sense. There's a better approach. That approach is design of experiments. And this example here, I think, will illustrate really what the failings of the one factor at a time approach are. So imagine this very simple case here where we've got two factors, pH and temperature. And we'd like to find a setting that maximizes the yield of our process. And so what the one factor at a time approach tells us to do is to start off at our best setting and then to vary one factor and keep the other one constant. So what we'll do is we'll fix pH at our best setting and then we'll vary temperature. So it looks like our current best setting, or what we think is our best setting, is a pH of 6.5 and a temperature of 30 degrees. So now let's fix temperature, let's fix pH at 6.5 and we'll vary temperature. So I'll do another run, another run, another run. So I've now done 5 runs, right, at 5 different temperatures. And we've managed to increase our yield from 33% to 55% here. So that's not a bad result. What the one factor at a time approach then tells us to do is to fix that factor at our best setting and vary the other one. And so now we'll fix temperature at 60 and we'll vary pH. So that's 6, 7, 8, 9 runs. And we've gotten now a new champion run. We've increased from 33% yield to 57. Some of you watching this are probably already recognizing some of the failures of what we've done here. So the problem is that we know where that best setting is, but how can we be sure that there aren't other settings within this entire design space that would have gotten even better yields? So there are huge regions of the design space that we know absolutely nothing about, and we can never be sure that we found our optimum. So what we don't know is that if we had somehow managed to get into the top left corner over there, that we would have gotten even higher yields. So using the one factor at a time approach, you could have gotten there eventually if you had fixed pH at 7 and then, you know, varied temperature again. Eventually you would have snaked your way up there, but it would have taken a lot of time. It would have taken a lot more runs, and you never would have been sure that you were actually at your optimum. Now, this is what happens when we have two factors. So you can imagine how the situation quickly gets complicated when you have 4 or 6 or 10 factors, right? And this is why people do thousands of runs, never quite able to predict how close they are to an optimum, never sure when they're there. So the reason the one factor at a time approach often fails is because it assumes this behavior on the left, where what you'll note, so here you've got concentric rings of increasing performance, increasing yield. And as you can see, you know, if you just look with your mind's eye, if you start at a pH of 6.5 or you start off at a pH of 7.5 and you move across and then move down, you'll always end up at the very center here, the point of highest yield. In fact, the behavior of systems is very often more complicated than that. You end up getting behaviors like this on the right. And so here, where you end up using one factor at a time approach depends on where you started your experiments. And so if you could take those 9 runs that you had done before and chosen a better position for them, this might have been a more efficient use of those 9 runs here, right? So now we maximize what we learned from the entirety of the design space. So this is called a full factorial design of experiments. It's 2 factors, temperature and pH, and 3 levels per factor. So each factor has a low setting, a high setting, and then a midpoint. And we've done every combination of each factors. The full factorial experiment was invented in the early 20s by Ronald Fisher. He was trying to solve a problem on crop yields. He was trying to figure out how they can maximize the yields of crops. And a short while later, someone had figured out that they don't actually need every combination. We don't need to do a full factorial experiment. We can remove some of these combinations and still get most of the information out of our design space, enough to understand which factors are important, which ones aren't. So that's called the fractional factorial. So now designs are getting more efficient from their conception. Then a little while later, somebody had figured out what the exact right or best placement of our points are if we want to optimize a process. This is called the response surface model, RSM. Then somebody figured out how to apply this to mixture factors that don't necessarily vary independently of each other, but are just concentrations within a mixture, and so on and so on and so on and so on. So there have been lots and lots of development and advances in design of experiments since it was started to be used just about 100 years ago. So hopefully that clears up for some of you who haven't seen this before, why the one factor at a time approach often doesn't work and why design of experiments is increasingly being used. And so what I'd like to do now is just take a second to tell you about a moment from my past where design of experiments really helped me out. This is a real situation. This is about 5 years ago or so. There's me. And I was working on site, so that's overseas, helping a customer from the company that I had worked for set up this furnace. So this is a big furnace, and I was responsible for helping them develop their process. So how this furnace works is products enter one side, so they enter from the left and they come out from the right. What you're seeing here, these arrows, so this is not product movement, this is airflow. And as the products moved from left to right, what was critical was that these fans here be set in such a way so that the pressure in these zones, so there's zone 1, zone 2, and zone 3, the pressure here and here needed to be negative relative to the factory floor where the people were working. So this is because inside the process was hazardous and they did not want any material from the process contaminating the factory. It poses a safety concern. And so the pressure there needed to be negative, but they also wanted no flow within the equipment. And so the pressures on either side needed to be as close to each other as possible. This is measured at some point inside. So how can we set these furnaces, these fans, such that all these criteria are met? And by the way, they didn't know where they were going to operate the fans, so they needed some idea of how it would work if they changed the fan settings and so on. By the way, they're not doors in the front here. This was just left open so that products can move freely through it, right? So that's why it was important that all these criteria be met. So in order to solve this problem, someone had presented this as a proposed experimental plan. So here's the first fan, the second fan, and the third fan. And they said, let's set these settings, wait 10 minutes for the tool to stabilize, record the pressures, and then move on. So change the setting, wait another 10 minutes, and so on. So I looked down, I said, how long is this going to take? And they said, well, it's 216 runs, right? They didn't say it like this, but what we're looking at here is a non-randomized 3-factor, 6-level full factorial. They said it's 36 hours of continuous work. we expect to do it or we expect you to do it in 4 or 5 days. If you guys really kill yourselves, you can probably get it done in 3 days. And I was already, staying at a hotel somewhere. I wasn't happy about this. I said, I don't want to lose 3 days. And they said, well, we understand, but this is very important. It's critical this gets done. You may have to push your flight back. So this is not something I wanted to hear. So rather than doing this, what I decided to do instead was to design an 8-run screening experiment. You see that here. So 8 runs, waiting the 10 minutes between each run, means that it would take 1 hour and 20 minutes to do this experiment. And I put in these settings, recorded the pressures, as well as the pressure difference measured inside. And then I used JUMP to analyze this to find out which factors were important and which one weren't. Now, there's a lot of information on this screen, but the most important thing is probably this. So some of you probably know about p-values, and that p-values above 0.05 are significant. So it doesn't look like these fans are significant at all, but what I can do is I can remove factors that appear least significant. And as I do that, you'll see that all of the calculations are instantaneously redone on the page. And now we can see some things are significant. So as I move forward, removing factors that are insignificant, you'll see that fan 2 really didn't have any effect on these pressures or at all. Now that wasn't a huge surprise. Fan 2, which was this one here, was the smaller one. So now that I figured that out, it took me 1 hour and 20 minutes, I augmented the design, adding a few center points here like this, but keeping all of the information from the first set of runs that I had done. And then from there, I could ask JUMP to tell me what was my most favorable setting. So I'll do that by just asking JUMP to maximize the desirability. Now what you're seeing here is called the profiler in JUMP. It's a graphical representation of the model that we had built from the information gained from this designed experiment. And so now you can see that asking JUMP to keep these pressures negative, but ensure that the pressure difference from one sensor to another are as close to 0 as possible, we end up with these settings here. So this took 2 hours rather than the 3 days if we kill ourselves that was being proposed. And the nice advantage to it is that if we decide to change one of the settings later, that we can just go back and recalculate the optimal point. So this is one instance where design of experiments not only helped me out because it saved 4 days of work, I can get on my plane when I intended to, but it also saved the company that I was working for a lot of money, allowed us to deliver a working tool faster to the customer. This is one case where everyone benefited. So once you know about design of experiments, you know that these tools exist, you end up finding opportunities to benefit from their use. So what we're going to do now is we're going to go through a much more, of course, this example benefited me, but this one benefited this company to the tune of $100 million. Just before we go into that, I would like to take a minute to understand what's stopping you from using these techniques that you're hearing about. And so with that, Ben, can we take the second poll, please?
We can indeed. So hopefully next thing you should see on screen is our second poll question. So what is most preventing you from applying a design of experiments approach in your organization? Is it that you feel your needs are just too specific and a DOE approach doesn't apply to you? Is it that you don't have support from on high, so management don't necessarily agree that this is the right approach, and so you need to find some way to convince them? Do you not have the time or the resources? Are you simply lacking the statistical skills, or is it a case that you're lacking the tools that you would need in order to do this? So we'll give you a short while to get your opinion in on that. I can see the votes coming in quite quickly. So once again, do please make use of the questions box at the bottom of your GoToWebinar panel. You can fire off any question you like at any point throughout the webinar. We will have some time for Q&A at the end, but also we should be able to pick up a couple of these if we do have answers for you and send you an email later. There's one option that isn't in there that I can see that Trevor has already sent us, saying it's actually none of these because we use designer experiments already. Now, if you are already using a DOE approach, then we are delighted to have you here. Though all those resources I shared at the beginning will help you to get the most out of it. And Hadley is clearly an expert, a very good person to have with us. So can help you not just start using designer experiments, but really make the most of it to make sure that you're getting the most efficient approach to your own experimentation. I think that's probably enough time for people to vote. Let's see those results. It's a fairly even spread, but the one coming out on top there is not having the skills. So this is perhaps the statistical understanding or knowing how to use JMP software, for example, or whatever other software they have that they're trying to use a DOE approach with. Followed fairly closely at 24% with not having the tools. Now, once again, I mentioned this at the beginning, we did send out a link. JMP is available for a free 30-day trial. If you are looking around for the right sort of tools, then that 30-day trial could be really what tells you that this is the right software for you. So we sent you the link out. We'll put it out again towards the end of this webinar. It is at jump.com/en_GB for the language /download-jump-free-trial. So it does what it says on the tin. So if you go to that link, which again we will share with you shortly, then that's where you can pick up a copy of the software and see if that is the right tool for you. And that hopefully for 24% of people here, that could answer that question in a 30-day free trial. That is probably long enough. Hadley, is this again what you generally see when people first start thinking about using this approach? Are these the barriers that people most often have to get over?
Generally, yes, and they're easy problems to solve, of course. So not having the tools is an easy one. As you say, if you go to our website, you can download a free trial. As far as the skills, there are many resources. I think that there's some in chemistry world as well as on JMP's website. You can find lots of, actually, if I just go to the website here, and you click on Learn JMP, you can see lots of resources here, the statistical thinking course, as well as the Getting Started with JMP that includes a module on DOE as well. And I'll tell you a little bit more about some resources later. We find that people develop the skills faster when those around them are also trying them out and also trying to benefit from DOE. That comes down to management's buy-in as well. In that case, what we would encourage people to do is to start small. So in this case, you know, a company benefited to the tune of $100 million, but not all experiments need to be like that. It could be shaving a little bit of time off, finding a fan setting. So start small, but then broadcast your success is the advice we'd give to help other people to get interested in design of experiments as well.
If you want to help other people in your organization to understand the benefits, then of course you can share webinars like this one as well, where you get the benefit of Hadley's experience. So the webinar itself, you'll be able to come back and watch at any time, send the link to any of your colleagues who think would benefit from knowing more about the advantages of using design of experiments approach, and they will be able to watch the recorded version of this webinar. So we're delighted to have you here live, but that doesn't mean that you can't come back or let other people know who missed the live webinar that they can still benefit from Hadley's experience and from the power of the design of experiments approach in terms of how you can make your own research that bit more efficient. Thank you once again for filling in the poll. Back to you, Hadley.
Yes, absolutely. So let's now jump into our main case study, which was the success that they had at Novomer. And so what I'm going to do here is go into just a little bit of the background of what happened here. So this was a company that had been trying to bring a product to market. This was some sort of a carbon capture polymerization product. And they were stuck because they had a large number of factors. And it wasn't clear which factors were significantly affecting their process. And they couldn't see a way forward. And so what they did using JMP is they defined an efficient data collection scheme where they could collect some information and then explore it in a way that they could communicate with their stakeholders and with their decision makers. And from that, they were able to gain insight to successfully scale up this process. Now, what they found was at odds with what they believed or understood about the reaction mechanism at the time, but it ended up leading to a better understanding of the reaction mechanism. And as I keep saying, and I don't mind repeating, they ended up spinning off this line of the business to Saudi Aramco for $100 million. And so what exactly did they do? Well, they started out looking at a potential of 35 factors. So these are things that they thought might be affecting their process. They collected some data about those factors, and then they identified the top 10 factors using data mining tools available in JMP. So here you can see the 10 factors of the 35, which are most likely going to be significant in affecting the process. Now, why did they choose 10? They chose 10 because they knew that they could afford to do 21 experimental runs. And so if they thought they could do more runs, then they could have collected more factors. If they had a much tighter budget, then they would have had to choose less factors, make some tough decisions. They designed a 21 run experiment. And based on the results of this experiment, they were able to identify which factors were significant, right? So these first 3 factors ended up being the most significant, as well as the factors that weren't significant. And so they used the first 3 factors to find the optimal setting of their process to optimize the output, the quality of the output, and then the non-important settings to find ways of simplifying the production process. So these were the 10 factors that they ended up looking at. One thing to say about this is that, of course, the factors had real names. So the names like additive A and additive B were just what they told us in order to keep the process confidential and proprietary. But they looked at 10 different factors. And then what they did is they chose, or they used the data from their data collection, data mining, to choose appropriate low and high levels of these factors, so thereby defining the design space that they wanted to explore. Now, once again, they had real values for these. So if we look at temperature or pressure at the bottom, for example, so it's conventional just to put a -1 for a low setting or a +1 for a high setting, and then 0 becomes your midpoint. When you do the actual experiment, you put in the real values of the settings. So these were just dummy variables for use, that I'm using here just to make sure that the actual process stays confidential. So what we're looking at here is their completed 21 run design and the resulting profiler, right? The graphical representation of the model from this design. So once they generate this, all they need to do is complete. So these are the results here, the yield. All they would do is put in the first settings. So monomer, catalyst -1, 100% catalyst, no additives, and so on. So they do the first run, record the result. The second one, record the result. And once they finish, they can ask the software to analyze it. This is the results of the analysis. So what you'll notice here is that our first 3 factors really are the ones that make this process the most significant, or really are the ones that are significant. You can tell that because they've got steep slopes. In fact, this one is even curved here. So if I change these values to a low setting or a high setting, you can look here and see that it really does have a significant effect on my output. So I can use this information to find what these best settings are. I can do, it looks somewhere around there, right? So the rest of the factors don't appear significant. And you can tell that because their lines are very flat. So if I were to change additive A, for example, from 0 to low setting to 2 or its high setting here, that it really doesn't change the process significantly, right? It stays within its confidence bounds. Here are the confidence bounds. So what that means is that you can set these things to whatever values you like or whatever makes sense. So I can remove additive A and B entirely from the process and then use 100% bulk monomer. So now we've not only figured out how to make this process better, but we've actually figured out how to make it cheaper as well. That's 21 runs. And so what we'll do now is we'll just take a small step back, and I'll show you the steps to create this design and in JUMP and so on. What I'm going to do is I'm going to open up in JUMP my Design of Experiments tab, and I'm going to go to Definitive Screening Designs. So definitive screening designs are one of the modern design techniques that we had talked about before. They were near the end. And they're a good thing to use because they allow you to screen factors for significance and optimize the design in one shot. And so I'm going to click on this. And then here I can say what my response is. So in this case, it's yield. Just add yield there, which I want to maximize, so that's fine. If I had more responses, that would be fine. If I wanted to change the goal here, if I wanted to minimize something, that would be fine as well, or match a target, but I'll just leave it as maximize. And now I'm going to add my factors. So the first factor was monomer / catalyst, which goes from -1 to 1. Now, I can continue to add these factors manually, individually, but what I've done is I've just saved these ahead of time here, so that'll save me a little bit of typing. Just go ahead and load those factors. So there they are. So now I've loaded in all my factors. I've defined my low and high settings for each one. I'll then press continue. I've got some options here. If I need to split this design up into different days and stuff, I can add blocks, but that's not necessary now. If I believe that my process is very variable, then it may be a good idea to add extra runs to better estimate the noise, but I'm not going to do that. I'll just set that to 0. I will then make the design, and that's it. Here's my 21 run design. So all that's left to do now is to run the first set with these conditions, record the value, record the second, do the second set as well. And then once I'm done, I can have JUMP analyze the results for me. So I'll just press make table, and that's it. All I need to do now is give this table to somebody on the production floor. They can do the first settings, record the values, and then give it back to me to analyze and create the profiler. So that was how Novomer were able to take a large number of factors, reduced to a slightly smaller number. So here's 10 factors, and then using only 21 runs, we're able to optimize and reduce the cost of their production process. And I've got a small document here. This was, I think, the press release from when the technology was spun off to Saudi Aramco for this amount. So not a bad result for 21 runs. So now I think that a lot of you, at least for me, really hits home what the potential value of design of experiments really can be. And of course, it can even be much more than this if we're talking about drugs, leading drugs or anything like that, if we're competing for patented drug ahead of a competitor. So there are some people that have done very, very well using design of experiments. But now the question arises, once we've designed our experiment, once we've conducted the experiment, once we've analyzed the results, how do we ensure that that information stays within the organization and doesn't get lost? A lot of times companies waste time and they waste resources trying to redo work that's already been done simply because they didn't know about it. So what I'm going to do now is I'm going to open up this case study here, which will appear on the screen. Yeah, so this first part is an example of a typical situation that is a reality in many companies. And as I said, it wastes time and money, it results in missed deadlines, and it's the exact type of problem that you want to avoid. So imagine this situation. So you work for a large manufacturing company with sites all over the world, and management has informed you that a decision was made to build a new line for a product that had been previously made in a different country. And they'd like you to manage the heating stage for the new line. So that's in addition to the work you're already doing. So the process manager from the old line sends you the machine settings. There they are. They say, we've been running this for a few years, and we achieve efficiencies of about 31%. So they're the settings. So what do? You put these settings into your tool, and you run the first test batch on a Monday. It takes a couple of days for the results to come in. So in the meantime, you run a second batch. Eventually, the results come in, and your average efficiencies are quite a bit lower. They're at 22%. So that's a 29% drop about. So you report this news to your boss, and she tells you that executive management were expecting a drop as we change lines or try to upscale processes from R&D into production. Often there are drops in performance, but they were expecting something like 5% or less. That's what they were budgeting on. So you're going to have to fix this. Okay, so successive batches aren't any better. And now, in addition to your current work, you have to rework this process in order to try to meet their timeline. So what you start to do is you start to go through every aspect of this process, looking to see what's different between your the way you're running it, the way they were running it at the old line. This is a very tedious process, as you can imagine. You've got a deadline, you've got other work piling up. Eventually, you figure out that the material grade that you're using is slightly higher. So that's fewer impurities than they were using at the other company. Unfortunately, you don't have the option of using the same material as they were using. So you reach out to the process manager from the other plant and say, do you know anything about this? He says, yeah, I think I remember us trying something about material and purity grades a while ago. I'll tell you what I'll do. I'll dig up the documents and I'll send them to you tomorrow. So of course, tomorrow comes and goes and you don't hear from him. So you reach out again and you get a reply immediately. So now what? Well, you ask a few other people, but they have no idea about any of this. So you start looking through the documents yourself, at the same time varying the process settings, hoping for some sort of an improvement. So you're running out of time, and all the while you've been neglecting your other work. Finally, you hear from the process manager, you can't find the documents, but somebody thinks they remember temperature being important. So you've been at this now for 6 weeks. You've got a deadline in your other work. You're frustrated that this has taken so long. You've basically had to develop an already existing process yourself, and it's still not ready. So let's look at an alternative now. This time, instead of sending you the machine settings, they point you to a link on an external website, and they say, this is what we use to figure out how to run our process. So I can click on this link because I have it embedded in my PowerPoint. You can't, of course, but what you could do perhaps is if you have an iPhone, you could take it out, and if you open up your camera app and point it at that QR code, then you can follow along. If you have another type of phone, maybe you know how to do that. And it helps if you hold the phone in landscape mode, it's a little easier to see. So this is well, in our story, a link to an external secure website. He says, this is what we used to optimize our process. So looking at this, you might recognize it as being a jump profiler. And by the way, this is a public version of this site, but of course, if this had been real life, it would have been on a secure site somewhere. You'll notice immediately that material A is included in these settings, and it's set to 4%. So since this is your process, maybe this is something worth checking. And when you do check it, you see that your material that you're using is 3%. So using this profiler, what you can do is you can grab this line here. So this one, me with my mouse and you just with your finger on your phone. If you're following your tablet, you can grab this line and move that all the way down to 3. And as you do it, you'll notice that this temperature in zone 1 profile seems to be changing shape. So it looks like now that you're using material impurity 3%, that this high temperature may not be the best setting anymore. So what do we need to do? So let's together solve this problem. Let's grab this line and move this over to find a better spot. It looks like just about there, somewhere around 48 degrees. So we're a little lower than they were at their optimal setting, but we're doing much better than we were before. So what do? So you inform your boss about this, and that's when she tells you about management's 5% limit. She says, if you can just make efficiencies above 30%, that's fine. So you inform the people running the tool, say we need to turn the temperature of zone 1 down 12 degrees. You get yourself a cup of coffee, and then you get back to your other work. So what are the key takeaways of this here? Centralizing, safeguarding, and distributing knowledge in a format that can be understood as a common challenge in many places. And it's even more critical when workers are required to interact with colleagues or customers at different locations remotely. Time and money can be wasted, and trying to gain knowledge that already exists within the company, but that nobody knew was there. And this can lead to delayed project milestones, cost overruns, or even frustration among employees. So what Jump Live does is it provides this framework for you to build knowledge repositories so that users can share and access knowledge when it's needed. So just wanted to tell you about how we can retain knowledge from designed experiments once they're completed. Like to thank you for your attention. Just to mention, we've already mentioned quite a few resources, and we'll mention some more, I think, but wanted to let you know about this book. So this was what really helped me to understand design of experiments when I first started learning about it. So just to mention, Brad Jones is the inventor of one of the inventors of definitive screening designs that Novomer had used. And then Peter Goose is a leading researcher in design of experiments. He's based in Leuven. So great book to start out learning some of the design experiments approaches. And then the other resources I think we've talked about. So with that, I'd like to thank you all for your attention. And now I think we have a little bit of time for questions. Is that right?
We do, yes. Thank you ever so much. It's been a fantastic presentation. Before we just get into audience questions, one of the resources that we should highlight really is the 5-part series that we did very recently. In fact, what I'm going to do is just show my screen so you can see the page. So this is available at the link that I'm about to send to absolutely everybody, but it's chemistryworld.com/collections/design of experiments. This is a 5-part course. It consists of 5 webinars that are very similar to today. There's demonstrations, there's bits of video, there's explanation of how the statistics work and how we can make the most of it. But also, as part of the course, you'll see on the screen now there are homework resources. And these are, they're not assessed, they're not marked, but they're a really useful tool to help you capitalize on your learning so far. So that is available at the link I've just sent. It will be available for quite a while. If you complete all 5 sections of the course, you then hit this button up here and you'll claim a certificate that can be used for your continuing professional development as well. So do check that out. If today's webinar has piqued your interest in GoToWebinar and it's in design of experiments and the approaches that you might be able to use to make your own work that bit more efficient, then this course is a really good next step to really properly understand what it is that we're doing. But let's move on to your questions. And you have asked plenty of really good questions, but do please keep them coming in as well. So let's go for this question from, it's a nice introduction question from Femi. Can JUMP be used for all sorts of experiments, or is it only really appropriate for any one particular type of reaction? Thank you, Femi.
Very good question. So JUMP can be used for all different types of experiments. We looked at 1 or 2 cases in particular, but it's used for a wide range of applications. You can see some of those listed on the JUMP in action page, as I talked about, but really good question.
We've just had one come in from Mohammed as well. He said, how can we use a response surface design for 3 factors where the response, for example, is yield?
If we're doing a response surface design for 3 factors, what I would use is the optimal design platform in JUMP. So if you open up JUMP, go to DOE and then optimal design, then you can put in your 3 factors. You can put in yield as your response and then specify your response surface model. So that's how I would approach a problem like that.
Excellent. Thank you again, Mohammed. Aziza says, if the design space changes over time, so if extreme values are different from our initial settings, can we use augmenting to design a new design of experiments with fewer runs? Is that something that's within our capability?
Absolutely. And you don't need to throw out the information from your old designs as well. So thinking about my tool example, so we were selling prototype tools that could be heated to very high extremes. What I would encourage people to do is use settings that they thought were safe, and then allow the results of their designed experiments to guide them as to whether they needed to turn every node up as high as it goes before, on the first day that they get the equipment. So yeah, what we see people is looking at a design region that they understand and then using the results of that as a guide to find out whether they need to shift the design space as they augment. So yes, that's entirely possible, and yeah, really good question too.
Ankit, now this is quite a broad and general question. I think this speaks to the way that the chemical community is changing, and the way the scientific community is changing. Is JUMP and a design of experiments approach feasible for an undergraduate student to start using?
I don't see why not. It's, as you saw, it's quite simple to use. Going through some of the resources, some of the online resources we provided, you'll see that it doesn't take much work to onboard yourself to get to a point where you can run designed experiments efficiently. I remember that I actually conducted my first designed experiment within 3 hours of learning that designed experiments existed, and then analyzing the result the afternoon after it had been done. So anytime you have factors that you can identify that affect an outcome, is an opportunity to benefit from designed experiments.
Excellent. A few more good questions coming in. So Vandana says, do we need to have some values for our factors before we start designing our experiments in Java. I guess this is about setting that initial range and so on. What do we need to have to make a start?
Yeah, well, in Novomer's case, they were lucky that they could benefit from some historical data that they could use to inform their design. That's called data-driven design. The reality for most people who are starting a design cycle is that they don't have this information. And so in that case, what they can do is they can go back to their own theoretical knowledge of the process. So they can think about or brainstorm settings that make sense that they would like to try, and like that define a range. In my previous example, I encouraged people to define ranges that were physically safe to run on this equipment, and then based on that, decide whether they needed to move. So that's how you can define the design space of a series of experiments before you've collected any information.
I see. And if you have a lot of factors that may influence the result, how do you know how many you should include in that initial design?
Yeah, good question. Basically, it comes down to how many runs can you afford. So how many experimental runs would you like to do? If you know how much it costs to do each one, if you know how long it takes to do each one, then you can say, okay, we would like to do this many runs. And from that, you can work backwards and see, okay, how many factors can we include in order to not go over our run budget. So if you look at too many factors, then your run, you'd need more runs to do it. Often what I encourage people to do is to start out with a small number of runs and a small number of what they think may be the most important factors. And then based on that, they can augment their design and add factors as they move on. Now, having said that, this definitive screening design that we talked about is a very efficient approach and allows you to look at a large number of factors with a very small number of runs. You saw in the Novomer case, it was 10 factors and 21 runs. But it really comes down to decisions between time and cost, and the importance of getting the knowledge as quickly as possible.
So we've talked in relative abstract there. William has sent us a very concrete example that hopefully will help to consolidate some of this. William says he manages a 4-step process, which is generally not very well optimized or understood. So a prime candidate for using a design of experiments approach to optimize it. So they're unable to predict product quality until after step 4. So would you design a design of experiments run to cover all 4 steps at once, or would you optimize each step? And each step has 5 factors, but the major issue is time. So how would you set about solving that problem for William?
I would look at all 4 steps simultaneously. Anytime you have something from one of your steps that affects your output at the end, so that's something that you'd want to keep track of and control and understand better in a designed experiment. If you have 5 factors per step, and you have 4 steps, so that's 20 factors, so that would be 41 runs using a definitive screening design. That may be an option for you, so that's one way that you can do, many factors with reasonably small number of runs. If that's not possible, then what you might do is consider which factors you believe are most important, most critical, and which ones aren't, and then focus your designed experiment on those. That is the approach that I would take, but I would consider everything that I thought might be significant. I wouldn't remove it from an experiment just because it was, happened to be in the first step or happened to be in the third step. I would look at all the steps at the same time.
William, drop us a line if you would like us to put you in touch with Hadley. I'm sure that Jump would be more than happy to help you to really make the most of your own work there and to do those optimization steps that you currently aren't able, you can contact us at cwwebinars@rsc.org and we can put you in touch with Hadley. Likewise, if you have any feedback, comments about webinars, just drop us a line on that email address. We've got about a minute left, but let's fire one last question. We've talked a lot about using JMP for running experiments and for optimizing processes, but you did also mention that it's a useful project management tool. So, does that mean you can use it to help set deadlines, set budgets, and so on? Could you just give us an overview of the other powerful things that JMP can do?
Yes, absolutely. So if you're using the one factor at a time approach, it's impossible to tell how close you are to optimizing a process. You never know when you'll be able to finish a series of experiments, when is something good enough, and it's impossible to budget for that or to allocate resources effectively ahead of time. If you're using designed experiments, like in the Novomer case, we say, right, we've got 10 factors we want to look at. So that means 21 runs. And so now if you know how much each run costs, you know how long each run takes. So now you're able to predict when you're going to get a result from your experiment, rather than simply saying, well, we really don't know how long it'll take. Let's just keep pouring money in, turning knobs and hoping for the best. So design of experiments allows you to make that decision ahead of time.
And that's yet another thing you can tell your managers as a good reason to adopt this as an approach if you are using that more traditional one factor at a time approach at the moment. But we are out of time. Hadley, thank you ever so much for joining us. We really appreciate it. We've worked with JMP on a number of different webinars. We've still got plenty more coming throughout the year as well. So do keep an eye out. We'll send people emails with all of the resources that we've shown you today. You'll get an email with all of these links in, but they are on screen again now. If you just want to quickly jot that down, statistical thinking for industrial problem solving, there's a course there that you can attend. JMP again is available as a free trial, so you can have 30 days to really see how this can revolutionize your own work. And that JMP community is there if you're looking for ways to make the most. If you're already a JMP user or if you're still thinking about it, that community of like-minded people, genuine researchers in industry and academia who will be able to tell you how they've made the most of it and share some of their tips and tricks for making the most of it. So once again, a huge thank you to Hadley Myers from JMP. Thank you to JMP themselves for organising this, getting in touch with us and being such an active partner in everything that Chemistry World webinars do. Do keep an eye out for future Chemistry World webinars. You'll find them at chemistryworld.com/webinars. You can re-watch this. We'll send you a copy of the recording. So if there's anything that you wanted to go back and watch again, don't worry, that will be in your inbox in the next few days. Along with everybody who attended, will get that certificate. It's our little way of saying thank you for joining us live for this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor, and we will see you again for the next Chemistry World webinar.